A candle flame can be detected from 30 miles away on a dark, clear night. That's the absolute limit of human visual sensitivity. Yet the same eye adapts within minutes to a room 10,000 times brighter or darker. The boundaries of what we can sense, and how quickly our senses adjust to changing conditions, are governed by precise psychophysical laws that reveal just how remarkably calibrated the nervous system is. The absolute threshold is defined as the minimum stimulus intensity needed for a person to detect a stimulus 50% of the time it is presented, not 100%, because detection near the threshold is inherently probabilistic rather than a simple binary switch. Classic psychophysics research established astonishingly sensitive absolute thresholds. A candle flame seen from 30 miles on a clear night, a ticking watch heard from 20 feet in silence, a single drop of perfume diffused through a 3-room apartment, and the wing of a bee falling on your cheek from 1 centimeter. The difference threshold, or just noticeable difference, is the minimum difference between two stimuli that a person can detect 50% of the time. Unlike the absolute threshold, which concerns detecting a stimulus's mere presence, the difference threshold concerns detecting change or difference between two present stimuli, noticing that one weight is heavier than another, or that one light is brighter than another. The just noticeable difference is not a fixed quantity. It scales with the intensity of the original stimulus, a relationship formalized by Weber's law. Ernst Weber's law states that the just noticeable difference between two stimuli is a constant proportion, rather than a constant absolute amount, of the original stimulus's magnitude. This explains a counterintuitive everyday experience. Adding 1 pound to a 1-pound bag is easily noticed, but adding 1 pound to a 50-pound bag is not noticed at all, even though the absolute change is identical. The Weber fraction differs by sensory modality, roughly 2% for detecting changes in pitch, but around 8% for detecting changes in brightness, reflecting different sensory systems' differing precision. Weber's law has extensive practical applications beyond the psychology laboratory. Retailers exploit it in pricing strategies. A $5 price increase is barely noticed on a $500 item, but keenly noticed on a $10 item, following the same proportional logic. Audio engineers use it to design volume controls that increase in perceptually equal steps rather than equal absolute increments, since equal absolute increases in volume produce progressively smaller perceived changes at higher volumes. Food and beverage companies use Weber's law when testing how much a product's recipe can be altered before consumers detect the change. Sensory adaptation is the diminishing sensitivity to a constant, unchanging stimulus over time, occurring at the level of sensory receptor cells and early neural processing. This is why you stop noticing the smell of your own perfume after a few minutes, stop feeling your clothing against your skin shortly after dressing, and stop hearing a persistent background hum after sustained exposure. Sensory receptors are fundamentally designed to detect change, not to report constant, unchanging information indefinitely. A stimulus that is not changing carries no new information worth continuing to process. Sensory adaptation serves a clear evolutionary purpose. Constantly processing unchanging background information would waste enormous neural resources and cognitive attention on stimuli that carry no actionable new information. By allowing the nervous system to essentially tune out constant stimuli, adaptation frees attention and neural processing capacity to detect novel changes in the environment, a sudden noise, a new smell, an unexpected movement, which are far more likely to signal something requiring a response, whether an opportunity or a threat. Adaptation is the sensory system's built-in filter for prioritizing what actually matters. Absolute threshold, difference threshold, and sensory adaptation together reveal that human sensation is not a passive recording device, but an active, efficient filtering system, exquisitely tuned to detect the faintest meaningful signals while automatically tuning out the unchanging background of everyday experience.